cry all you want. It's sometimes it feels good to get a little bit of cry. Okay, sometimes I have to curl up underneath my desk and just cry myself in the fetal position because I'm like chemo from that movie Stand and Deliver. Calcules.
If it actually has humans in the.
You don't watch humans?
I watch animation.
Only anime.
Only pixelated humans.
Pixelated humans.
So like.
Come on, the guy's like, Ole, finger man. I know nines. 9 times 5. 1, 3, 4, 5, 14, 5. That guy? No. How do I get through to these kids? South Park even did it too.
I don't watch South Park.
Oh, okay. Fine, forget you. All right, let's try it again. Class.
Yes.
Thank you. All right.
Is this
So,
study group again?
yes, this is study group today. Thank you very much. Okay. All right. Now, trig identities are easy. I know everyone probably had a horrible teacher last year, except for you, but trig identities are easy. They're either sine or cosine. That's it. All 6 identities are derived from sine and cosine. So we're going to take a look at tangent. We know tangent is... No, I don't want derivative. What does tangent actually represent? Sine over cosine, right?
Oh, tangent.
Yes,
okay.
Tangent, not just tangent, but tangent. It implies that it is sine over cosine. There you go. Now, by looking at that, I should be like, oh, hey, I don't know how to do the tangent by itself, but I know sine over cosine is a quotient rule. So if I say that that's a quotient rule, that this is going to be my f and this is going to be my g, insert page. Okay, so f prime, what would f prime be? Yeah, it's cosine theta, hold on. Cosine theta, and g prime. What's the derivative of cosine?
Negative sine theta.
Negative sine theta, very good. Alrighty. So we're going to do quotient rule, and my quotient rule is it's f prime g minus g prime f all over g squared. All right, f prime is going to be cosine. So cosine theta times g, where g is cosine theta. Yes? Minus g prime is going to be negative sine theta times f, which is sine theta. All over g squared, which is cosine squared theta. And if you notice, okay, the notation of this cosine square goes here because there is a difference in between this and cosine of theta squared. That's going to be a big difference right there. I don't want you to misconstrue those two, but this would be the same as saying cosine theta squared. So this one right here is a no. This one down here would be a yes, and this one up here where the square is over the s, that is also yes. That's implying that the cosine is squared, not the theta by itself. So I just wanted to throw that out to make sure everyone knows where and why. Now, I love this. I love this because this is beautiful. I really do. I have minus a negative. What happens there?
Positive.
Changes to a plus. What's cosine times cosine?
Cosine squared.
So it's cosine squared theta plus sine times sine?
Sine theta.
Sine squared theta all over cosine squared theta. That is 1. Good job. That is 1. Cosine squared plus sine squared is going to give me 1. So that turns into 1 over cosine squared theta. So my derivative tangent, so if my function, what was the notation? Okay, so it was y. Okay, so I'm gonna do the other notation on this one. So dx of tangent x is equal to, since I did the quotient rule on this, it's going to be 1 over cosine squared theta. Now, got to go way back. 1 over cosine. 1 over cosine, anyone, that's a reciprocal identity. It's a reciprocal of secant. 1 over cosine is secant. So 1 over cosine squared is secant squared. So it's the same thing as saying that this is going to be the same as secant squared theta. So both these answers work. Both answers here are correct, but we normally just use the second one. That's the reason why when you look at an identity sheet or one of those cheat sheets that actually have all the derivatives already, it just goes straight to secant squared theta or secant squared x. Make sense? Nonsense? Hopefully. Good. Now, so if we're looking here, here's all your derivatives that you've been needing. So derivative sine gives me cosine, derivative cosine gives me negative sine, derivative tangent is secant squared. Now some of these other ones are kind of weird, but same thing works out. So if you want to do the quotient rule for cotangent, because I know cotangent, what is cotangent? What is just cotangent supposed to be in the first place? What over what? Sine over cosine?
Cotangent?
Cotangent is cosine over sine. Because tangent is sine over cosine.
Okay.
So cotangent, I flipped it over, it's cosine over sine. So this is the same as cosine over sine. So that's one way to actually do it. So I could do the quotient rule to get that one. Now, cosecant is the reciprocal of 1 over sine. Very good, 1 over sine. So I could also do the quotient rule to find out this one as 1 over sine. I could do that to get this identity. The reason why I say identity is we don't have to go through and do it every time. You should be able to say, hey, look, what's the derivative of tangent? Secant squared. You don't have to go through and do it every time. You should be able to identify it as what the derivative already is. That's what an identity is. So something here, automatically, you don't have to do the math to go all the way there. But if you want to do the math, you can. And secant, derivative secant, because secant is 1 over cosine, it's a quotient rule again. end up with secant times tangent. Make sense, or is that nonsense?
Some sense.
Some sense. And domains of derivatives. This is important. Domains. Now, what is the domain supposed to be? What does that mean?
The X.
X values, right? X values that I'm allowed to use. What values of X am I allowed to plug in for this to still work? So, this notation, okay, for these first two, since sine and cosine are waves, it goes from negative infinity to positive infinity. For these other ones right here, and it says X such that X cannot equal to 2k plus 1 over 2 times pi, where k is an integer. What that means is I cannot have 0 in the denominator. That means cosine cannot be equal to 0. So, because I know that secant squared is 1 over cosine squared, right? And cosine can't be equal to 0 because that would give me undefined for my derivative. So everywhere that cosine is going to give me a 0, that's what that means. Everywhere that cosine is going to give me a 0, x such that x, so every time that this is going to be over 2 pi, it would be 2 pi. So it's odd numbers of pi over 2. 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Does that make sense? Or no? Unit circle.
Yeah, unicircle, please.
So this up here is pi over 2. The coordinate is 0, comma 1. This one over here is 0, comma negative 1. And this one is 3 pi over 2. So as we're going around, that's the odd numbers. So if we go to here, it cannot be here because that would mean cosine, which is my x value, is going to be 0. So in the domain, I cannot have that. So that's what that means. X such that x cannot be these, and k is an integer where it is going to end up becoming odd numbers here. And it also happens over here, and every time it just keeps coming back up here, can't be there. So it's going to be a hole in my wave. These are all waves, and these are all going to be holes for this. All right, same thing goes for the next one. For cotangent, that one's going to be, let me see, negative, so that's going to be a sine. So that's where everywhere that the y value is going to be 0. So that's going to be 1 comma 0. That's going to be in terms of pi, so that would be right here. And this one also, this is 0 pi, this is 1 pi, 2 pi, 3 pi, negative 1 comma 0. So basically everywhere that it's going to give me a 0 in the denominator as I look at these. All right, evaluating second derivative of a trigonometric function. Find f double prime. So I'm going to take the derivative and then take the second derivative. So I'm going to do the derivative of the derivative. So if f is equal to secant, okay, go look at the previous problem. Actually, now let's go ahead and do this one. So if f of x is secant, which is 1 over cosine x, let's actually do the quotient rule on this one, see if this helps. So if it's that, I know that my f is going to be 1. F prime is, what's the derivative of 1? 0. G is cosine x. G prime is negative sine x. All right, let's go ahead and quotient rule this one then. So it's f prime times g, which is cosine x, minus g prime, negative sine x, times f, which is 1, all over g b squared, which is going to be cosine squared x. All right, negative, negative. Two negatives, going to make that a positive. 0 times anything is 0. Thank you. All right, so this cosine is going to go away. And then it's just now negative, negative, make that sign be a positive times 1, which is a sine. So I'm going to end up with just sine x on top and cosine squared on bottom. But cosine squared means I have a cosine times a cosine, right? So I'm going to rearrange this a little just to try and make it fit what my identity on the previous page came up with. So it's sine x over cosine x times cosine x. Sine over cosine is? Sine over cosine is? Tangent, very good. So this becomes tangent. But now over here, what's left on top?
1.
There's still a 1 right here, right? So this is still a times 1. So this is going to be 1 over cosine. 1 over cosine is? Secant. So it's tangent secant, or if you want to put it the other way, secant tangent. There it is. So we just did the quotient rule because I know the quotient rule and I know sine and cosine. Okay, if you know those things, all these other derivatives you can get by using the quotient rule. And just so you know, I totally forgot these ones here, down here on the bottom, because every year when I teach this, I forget this. I don't use this often enough. I forget this. But every time I go through and I do the quotient rule to refresh myself how to do it, and then it helps me from there. I don't memorize all, I can't even remember how many regular trig identities there are for the Pythagorean identity. There's 6 Pythagorean identities. I don't remember them all. I remember one, and I know the math to get the others. Because it's all like a whole bunch of different variations of the same thing. Just do the math to make it match what you have. So that's the best way to try and look at it. It's not always going to be a solid thing. It's make the math work for you is the best way. Because rote memory doesn't always work. All right, so there's my first derivative. So I have tangent times secant. So that means that f prime of x is tangent x secant x. What rule is this?
Product rule.
It's a product rule, right? Tangent times secant is a product rule. So that's going to be a product rule. So now let's look at it. So f is tangent, g is secant. F prime. What's the derivative of tangent? I can go back through and do it again, or I could just look at the sheet that I already did this. What's the derivative of tangent? Didn't we just do that?
Yeah.
Wait, hold on. Isn't this whole thing the
Secant
derivative?
square x.
Okay. Derivative of tangent, right there. Secant squared x. There we go. So You don't have to do it yourself every time. You can go back and look at your own work of where you did it before. So we have secant squared x, and then g prime. So the derivative of secant is didn't we just do this right now? Yes, we did, didn't we? Derivative of secant is secant tangent, right? Secant tangent. There we go. So now all I have to do is plug this into my product rule. I go off to the side, identify my different parts of my product rule, and now all I have to do is plug these into my product rule. And product rule again is going to be f prime g plus g prime f. So f prime, that means I'm going to have secant squared times g, which was secant, plus g prime secant x tangent x times f, which is tangent x. Yes, no, maybe? Okay. All right, I'm going to do a little bit of grouping together, because what's tangent times tangent? Tangent squared. Okay. And what's secant squared times secant? Secant cubed. Very good. So we're going to have secant cubed x plus secant x times tangent squared x. Okay, so I could leave it there. Can you identify anything I could factor though? They both have a secant, right? Okay, let's see if that helps me with anything. So, answer is correct starting here. It's still correct here, but I'm just looking to see if I could do something else to simplify it. So secant x, and then it's going to be secant squared x plus tangent squared x. Whenever I see a secant squared, tangent squared, if I see any of those squares, I always want to try to, like, okay, again, I don't memorize all the trig identities for Pythagorean identities. I can try to make it. So what I'm going to do is, on the next page, I'm going to go, and I'm going to try and see if I can get my identities to work with this. So there's one identity I always know. I know that sine squared plus cosine squared is equal to 1. That is my Pythagorean identity. That's the first identity. Always. Yes? That's always the first identity. Sine squared plus cosine squared is equal to 1. Everything else is something from this. So if I have a tangent, what do I know about tangent? Sine over cosine, right? So can I make this into a tangent squared? Say yes. Okay, so I'm going to divide everything by cosine squared. So whenever I have something like that, and I want to make it into a tangent, I want to have sine over cosine, right? Tangent is going to be a key, because it tells me I have sine over cosine. Cotangent would also be a key that says I have cosine over sine. So I'm going to divide everything here by cosine squared. All right. Let's see if this works. What is sine over cosine? Tangent. So this first term is going to be tangent squared plus, what is cosine over cosine? 1. So cosine squared over cosine squared, still 1, equals 1 over cosine squared is? All right, so if I were to try to use this, what would have to happen over here? I have a secant squared plus a tangent squared. I would need a 1, but if you notice, are both of these positive here? Okay, so both of those are positive right there. And so if I were to go minus tangent squared, I would have 1 equals secant squared minus tangent squared. If you notice, I don't have my variables on there because this could be any of the variables, a t, a theta, an x. So it's kind of my shorthand for this. I always leave off those when I'm doing these, trying to identify my different uses. So is there a way that I can actually make it into a secant plus tangent? If I multiply everything by -1, would that help? Okay. Why no? Because if I multiply by -1, that means I would have a -1 out here equals negative secant squared plus tangent squared. It doesn't really help me, does it?
No.
It just changed where the negative was. Now, this practice of manipulating these things, even though that this one didn't work out, I wanted to have this in your notes here because you're going to have to do some of this stuff yourself when you're looking at some of these problems, because some of the problems are like, what the hell is that? A lot of times it'll simplify down to nothing. It will. It'll simplify down to nothing, and then you'll just be like, oh, okay. It gets a lot simpler. So whenever you see this identity here, when you see this, you know that you could replace secant squared minus tangent squared with 1. Or you could replace tangent squared minus secant squared, the second one, with -1. So these are different uses of the same identity. I'm just rearranging. They're all equivalent. All right, so that means that since it doesn't go any further, I'm going to leave this as my answer here. Yes? Good. All right. All right, last problem, I think.
You have like one more time.
Yeah. But how many parts does this one have? It's got 5 parts, so yes. All right, let's see. An object hangs on a spring, making the spring 2 meters long. In its equilibrium position, if the object is pulled down 1 meter and released, it will oscillate up and down. The length L of the spring after t seconds is modeled by the function. L of t is equal to 2 plus cosine t. Yes? Okay. So, how does the length vary? Okay, so how much, so if this is equilibrium, it goes up how much? 1, and it goes down how much? So the total variance is how much? 2. So it goes up and down 2. So that's how much it's going to vary. So this is 2 meters. Next one, velocity. What do I know about velocity? What is velocity? What do we say velocity is? What is velocity? It's a rate of change. And what do we know about rate of change? Rate of change is the slope, basically, right?
Yeah.
Okay. The basic word I was looking for was derivative, right?
Okay.
So, velocity is the derivative of the position. L of t is the length according to time. That's the position where it is in a certain time period. Where the derivative is going to be the velocity. And the absolute value of the velocity is, anyone recall what I said? We were talking about it. Absolute value of velocity. It is the derivative, right? It is the derivative. So, Denny, driving through the school zone, right?
Okay.
Okay, so he has a positive velocity when he hits that first kid.
Yeah.
All right, and then all of a sudden, after that, he has a negative velocity. What would that tell me if he now has a negative velocity afterwards?
He drove backwards.
Yes, he went backwards to go, over the kid a second time. Okay, negative velocity, that means he's going backwards now. But is he going back in time? No. Okay, so absolute value of his velocity is his speed. Miles per hour is his velocity, which is also his speed. So if he's going forward, okay, everyone's easy to understand, okay? He's doing 45 miles an hour as he hits that first kid, right? So what is the speed he's traveling? 45 miles per hour. Okay, then Denny changes it to a negative 45 miles per hour. Is he going back in time? No. He put it in reverse. Now he's trying to back over the kid. The kid was a jerk. He's like one of those little kids that give you the finger and they're like only 4 years old and then their parents think it's funny and they're like F-bombing you and you're like, you just like Sparta kick them in the face. This is Sparta, and like right in the face. Be like, ah. Yeah. Anyway. Are we good now? So absolute value of velocity is, did you already forget?
Yes.
Speed. So did you write that in your notes? Because it might be important. So the absolute value of the velocity is your speed. Velocity is the first derivative of position. Velocity is the first derivative of the position. So it says find the velocity. So that means I need to find the, say it loud and clear, derivative, right? Yes? Okay, good. We have to find the derivative. If it said find the velocity, I'm finding the derivative. That's what we're doing here. So L prime of t, what's the derivative of 2? 0, right? And what's the derivative of cosine? Sine. Okay, so now I have the derivative. Find the velocity of the object. Okay. What position is the speed of the object max? Think of those parabolas that we did when we're driving. Okay? So we throw something or we kick something. I think the problem is like we kicked it or something or threw a football or something. It went up, right? Yes? So it was going up. And then what happens after it's going up? The height max, right? Okay? And what's going to happen? It's now going to change. It's going to change from a positive to a negative. So a positive velocity to a negative velocity. So both in between positive and negative, what is right there in between positive and negative? Max and zero, right? I'm going to have a zero. Every time I'm looking for a change in between a positive velocity of Denny hitting that kid and then a negative velocity where Denny is backing up over that kid again. Okay? So, right there at the peak, there's going to be a zero. So at the maximum, I want to have a zero. So that's going to be my velocity equal, yeah, that's my speed, right? Okay, must be equal zero. Okay, so speed, right here, it's going to go from positive to negative. So let's see. Let's set this equals 0, equals, so this all part, was it part B, and then this part C. Did I have that right? Yes. All right, divide both sides by negative. That one should be easy. 0 divided by negative 1. Yeah. So I get 0 equals sine t. All right, let's see if you guys paid attention to me yesterday. If you're looking for an angle, you do the inverse. I do an inverse. So now, when is sine equal to 0? That's what I'm looking for now. When is sine going to be equal to 0? So I'm going to have that. Let me see. T is equal to inverse sine 0. So on my unit circle, when's that going to be equal to 0? Okay, in between where? So it's going to be 0. Where else? You skipped one. 0 pi, right?
Oh, 0 pi and then pi over 2.
No. Sine is the y. Pi. Yeah, you had 0, but if it's 0 here, it's also 0 over here, right? So it'd be pi, and then 2 pi, and then 3 pi, and so on, right? Okay. So those are the places I am going to have the max speed there. At what position speed is max? Find the acceleration of the object. Now, what do we say acceleration is? Very good. Acceleration is the derivative of the velocity. acceleration is the derivative of the velocity, just in case you forgot it. You didn't forget it though, right? Okay. So, Denny, okay, his velocity, 45 miles an hour as he hits that first kid. But now, when he hits that kid, his acceleration, is he increasing their speed or is he decreasing speed? Is he trying to hit his brakes or was he foot on the gas? Foot on the gas? I'm telling you, it's that a-hole kid. You know which one I'm talking about, right? It's like Bebe's kid. Okay, yeah. Anyway, so it's going to be the slope of the velocity. So acceleration is the slope of the velocity. Therefore, it is the derivative of the velocity. So we said so L prime of t was negative sine x. So the derivative L double prime of t. What is the derivative of negative sine? Use the circle. Negative cosine. That circle is super helpful. Sine, cosine, negative cosine, back to sine. Sine and cosine are waves, so therefore it just keeps going back in that circle. There you go. So I now have the acceleration, which is my second derivative. At what position is the acceleration equal to 0? Okay, let's see when the acceleration is equal to 0. Now, what would that mean if you're thinking about Denny and driving? What would it mean if his acceleration is 0? What do you got, Meow? Think about it. If your acceleration is 0, what does that mean? Stop. That would work. So if you're at a stop, okay, your acceleration is 0. Anyone else have a constant velocity? So it's not changing, right? So he's going through the school zone, cruise control on. So he hit cruise control 45 miles an hour, so it's neither increasing nor decreasing. A constant, right? There we go. So therefore, he is not changing in acceleration. So his acceleration would be 0. Because if it was increasing, it would be a positive number. If it's decreasing, he's slowing down, it would be a negative number. But right there in between, he's staying. He's not changing, increasing, or decreasing. Therefore, do it again. Divide by -1. 0 is cosine x. And if I'm looking for an angle, I do the inverse. X equals inverse cosine at 0. When is cosine equal to 0? Pi over 2 is one of them. Pi over 2, there we go. So unit circle. So it's right here, 0, 1, and 0, -1. So this is going to be at pi over 2 and 3 pi over 2. So this is going to be intervals of that. So every interval of pi over 2. So this is the odd interval again. Make sense? Nonsense? Good sense? Money? Cash money? Is that what that means? Cash money? I don't know that one. Just makes sense. Okay. All right. So, guess what? We are done. Guess why? Chicken time! Ha! See what you did there. See? Anyway, all right, make sure you all like, share, and subscribe. Hit that notification button and support my channel by use promo code HOLIDAYS. 10% off my merch store.